Okay, so you should have just viewed the video on the demonstration that between the reaction of the peroxide and the manganese dioxide as an example of the effects of concentration on the speed of a chemical reaction. Well, let's go back now and do the same chemical reaction. But this time what I'm going to do is I'm going to substitute the catalyst with a reactant, a different reactant. Okay, instead of having a catalyst, I'm going to actually use a reactant to see if I can produce the same result at the end of the water and the oxygen. And this reaction is a little controversial that I'm going to use because here what I'm going to do is I'm going to include sodium iodide. And again, this is a little controversial because some people say, well, the iodide is acting as a catalyst and therefore shouldn't be considered a reactant. But some people do have determined that some of the iodine is actually consumed in the chemical reaction. But in this reaction, what we're going to do is we're going to consider the iodide as a reactant. And at the end, you say, well, Mr. Joe, where is the iodide as a product? And what you typically would get, some scientists believe, is iodate ions produced as a product. And that's where the controversy is. But what we're going to do is we're going to treat the concentration of the catalyst. We're going to study the concentration of the catalyst. We're going to say, okay, it's a catalyst and there's no iodide produced. So we're going to take that assumption. So when you rewrite this, you want to have a plus here. The iodine would actually be over the arrow. So typically when you see a chemical written over the arrow, it's being considered a catalyst. And what we're going to do in this study is we're going to do the same reaction that I showed you a few minutes ago, and you'll see that we have the peroxide at different concentrations. We're going to do the experiment 3 times. So we're going to have 3 trials. And typically in kinetic studies, you always do your experiment more than once. And typically in kinetic studies, what you do is you do the experiment more than once. And why do you do it more than once? You want to vary the concentrations of your reactants and your catalyst to see if it has an effect on the speed of the chemical reaction. So in trial 1, we used a 6% peroxide solution with a 4 molar sodium iodide catalyst. In trial 2, we used a 6% solution with a 2 molar sodium iodide catalyst. So here what we're doing is in between trial 1 and trial 2, we're seeing how the concentration of the catalyst, does it play a role in the effect of the speed of the chemical reaction. And then between trial 2 and 3, trial 1 and 3, you'll notice that we keep the concentration of the catalyst the same, but we vary the concentration of the peroxide. We actually have the concentration of the peroxide. And what we did is basically, if you've paid attention to the data, we took an empty flask instead of a graduated cylinder. We weighed it empty. Then we put some peroxide in. And we got the mass of the peroxide. And you should note that we tried to keep the mass of the peroxide constant, okay, as best as we can. And then we have the mass of the mass of the peroxide constant. So you'll notice that you got 1.55 grams here, 1.54 grams there. So the mass of the peroxide here is the same. So these two typically, as best as we could. And then here we put half of the amount of peroxide, because remember in trial 1 and trial 3 we have the amount of the peroxide. And then what we did is we weighed it, we did the chemical reaction, and with your iodide catalysts, and we measured the mass of the peroxide in the initially and at a certain time, let's say 30 seconds. And at 30 seconds, we know the mass of the container changed. Okay? How much did it change? Well, initially, these were the masses at the start of the reaction. And I'm sorry, we used 50 seconds. I'm sorry, it was 50 seconds. And this was the mass at 50 seconds. So there was a difference, a mass loss. And the mass loss can only be due to the production of a gas leaving the cylinder. So in the first trial, we got 0.51 grams of oxygen produced. In the second trial, where we varied the concentration of the iodide, we added 3 milliliters to each trial at different concentrations. Okay? And we got 0.24 grams of oxygen. And in the third trial, we got 0.13 grams of oxygen. So in the first trial, we got more bubbles. A lot more bubbles. Okay? In the second trial, we got less. In the third trial, we got even less. What does that mean? Well, obviously, let's take a look at the numbers. That if you decrease the amount of catalyst, the catalyst concentration is playing a role on the amount of bubbles you're getting. How fast you're getting your bubbles in 50 seconds. So the concentration of the catalyst plays a role in the speed of your chemical reaction. So in this experiment, we see that the concentration of the catalyst is playing a role on the speed. So I want to write down concentration of iodide ion is playing a role in this reaction. So between trial 1, we can see that. By varying the concentration of the catalyst, we see an effect on the speed of the bubbles being produced. Let's look at trial 2 and trial 3. What was that supposed to show me? Well, I'm sorry, comparison of trial 1 to trial 3. Because trial 1, the catalyst concentration was the same as in trial 3. But we have the concentration of the peroxide. And if we look here, we see that it definitely produced a difference in the amount of bubbles in 30 seconds. We got 0.13 grams of bubbles in 30 seconds compared to the original 0.51 grams. So which of the chemicals, so we know now that the concentration of the peroxide also has an effect on the rate of the reaction. But which one has a greater effect? The concentration of the iodide or the concentration of the peroxide? And if you look at the numbers, we see that the concentration of the peroxide has a greater effect because it generated a lot less bubbles in those 50 seconds. So by having the concentration of the peroxide, there was a bigger effect on slowing down the reaction compared to the having the concentration of the catalyst. So that is what we typically do in kinetic studies. We take a look at how the varying the concentration affects the speed of chemical reactions. And there's a reason for that. Because what we do is based on experimentation and varying the initial concentrations of chemical reactions, we could come up with what we call a rate law. A rate law is an equation that basically allows us to, by knowing initial concentrations of reactants, figure out how fast the reaction initially is going to go. And say, why would I need to know this? Well, if you're in the business of producing products fast in order to make money, you would want to know what the rate law of that chemical reaction is. And the rate law is basically, it takes a format that the rate of a chemical reaction that you're studying is equal to the concentration of your reactants. In this case, the concentration of your peroxide. And we know the catalyst is involved in the effects on the speed. So he's included in the rate law. To the power of some number, some exponential, that you experimentally determine. These are called rate orders. So the x and y exponentials are determined experimentally through trials of experiments that you vary the initial concentrations of these chemicals times this thing called a rate constant. A rate constant is basically a number that's specific to your chemical reaction that tells us how temperature affects the speed of the chemical reaction based on the type of reaction you're working with. So every chemical reaction has its own rate constant. So all reactions have some sort of rate law. To get the rate law, you would have to somehow experimentally run trials on the experiment where you vary the concentrations of your reactants initially to see how it affects the speed of your chemical reaction. And you have to do the chemical reaction at the same temperature each time so that the rate constant would not vary. And we're going to show you how you do those kinds of things in class.